So let's start with the new chapter called feedback for the course called Analog Circuit Design E211. So let's start with the positive feedback multivibrators. First of all, there is one word called multivibrators. It's very popular. There are three kinds of multivibrators. One is called monostable, one is called bistable, and one is called astable multivibrator. So monostable multivibrator is the one whose output is monoshot. When I say monoshot, it's one impulse will be available at the output. So in that circuit, it might have VDD, ground, it might have some input also. And as an output, you're going to have this one. It's called monostable. But in the same place, circuit is similar, let's say, but the output is not like this, but it's a square wave. We are referring this kind of circuit as bistable multivibrators, whose output is either square wave or rectangle wave for a defined input or anything. However, there is one class of multivibrators whose output is a square wave or rectangular wave. However, there is no input. On the application of VDD and ground, the output should be giving me the square wave, or it's a 0 and 1. By the way, all such things which we are making, it's a class of circuits which we can call it oscillators. Notably, the output is either 0 or VDD. This is very much useful in in the circuits when you want to have the clock signal for digital circuitry, and it's a different class of study. It's called oscillators. So if you want to have the oscillations, you need to make sure that your circuit is in positive feedback. This is one thing. So if you are interested in making oscillators, means oscillators itself are unstable. Read that carefully. It's either 0 and 1. So it's not like an amplifier which were stable and having the phase margin more than 45 degree. If you remember, the phase margin was more than 45 degree to get the system stable. However, in such cases, the phase margin is poor or less than 45 degree, and you can observe oscillations which are growing one. When they are growing, let's assume that your output in terms of amplitude with respect to time, let's assume that it's growing. Such system is called unstable, right? But as we know that in all our system where it's governed by VDD and VSS or the power supplies, so output cannot go beyond that, or it will get stable, or you can say that it will act as a square wave. So it's saturated over here, and over the time you can see that one as a square wave, right? So such kind of system is oscillators, and oscillators have many problems and many things, but the design has some different uh, objectives other than amplifier. But most of the time, those who are making the amplifiers, where we want that it has to be stable and phase margin is greater than 45 degree and no oscillations, proper settling and all, if we want that, then most of the time students are landing up with making of oscillator, because it's very difficult to make amplifier at the first shot, so they're landing up with the oscillator, and you need to tune it such a way that it becomes amplifier. So all the bad amplifiers are actually oscillators, and all the bad oscillators are the amplifiers, right? So this is a one, we can say that irony, that generally those who are making oscillator, they'll end up with making amplifiers, and those who are making amplifier, it'll end up with oscillators. But you need to design it with one criteria of Barkhausen criteria for the design of oscillators. And we already studied how to make this amplifier stable or pole placement and all these things, so those has to be done carefully. So as I told you, the chapter name is feedback, but our main concern is not to focus on positive feedback, but our main concern to focus on the negative feedback, which is the case for amplifier. If it is positive feedback, look, the system is unstable, right? System is unstable means your output is either 0 or VDD. If you remember the the case when this one is a popular circuit, you must have studied before this course. If this is RF and if this is R1, the V out by Vn is equal to minus RF by R1. That is known to us. That is a, like, using golden rules of op-amp and all, you can use it and you can find out this very quickly. But look at these signs. This is negative feedback, by the way. It's not a positive feedback. If it is negative feedback, then and then golden rule works. However, if it is positive feedback, that circuit name, by the way, this one was inverting amplifier, but in this case when we change this, the answer is not same, by the way. But this circuit is known as Smith trigger, and it's always positive feedback, and as it is positive feedback, output is either VDD or VSS. So that becomes interesting thing. And on top of that, if you look at the input output characteristic, this follows such kind of characteristic. Look at this, and this create an hysteresis, by the way. The path which is taken from here may not be the same as the previous one, or it will have such kind of path. We need to find out whether it's coming from VDD to VSS or other way around, and through that you can find out these points when it's actually changing the state from VSS to VDD or VDD to VSS. And for that, particularly at this point, you have to use the golden rules. Golden rules are applicable only at point X and point Y. By the way, point X in Vin is not known to you. Input points X and Y are not known to you. However, at point X, you know that what is the value of, okay, I should have called some better name, A and B. I know what is the output value. At A, my output is traveling from VDD to VSS. Or for point B, output might be traveling from VSS to VDD. And at these points, I know that it follows the golden rule. And like, I'm very sure that you must have studied this this kind of circuit, how to solve it. So I'm giving you the answer in that case. So where it's following this golden rule at A and B point, I know that V out by V in is nothing but, when it's following the golden rule, we know the two golden rules which are saying that, one golden rule says that V plus equal to V minus and no current is flowing inside because of the high input impedance, low output impedance. All these things are known, but two main golden rules are known to us. Using these two golden rules, you can find out V out by V in is nothing but minus RF by R1. Only applicable at point number A and point number B. Note that it's not applicable for the whole characteristic. However, for solving such kind of circuit at point number A and B, this is the thing. And I know that what is happening at, like, I need to find out the point V in for which V out is becoming either VDD or VSS. So let's have the case when V out is equal to VSS. VSS is generally minus term, right? You can see that it's minus side below zero line. So V in is nothing but R1 divided by RF times VSS. So look at this. This particular result give us information that when V out is minus VSS, means V out is minus VSS, V in is equal to R1 by RF times VSS. However, this quantity becomes plus. So A is negative quantity where B is positive. So in that case, it is sure that this point has to follow this number, because we have only two possibility. A is negative and B is positive. So this particular number R1 divided by RF times VSS has to be point B. Whereas when V out is equal to VDD, V in has to be minus R1 by RF times VDD, which is negative quantity, and that has to be point A. So these are the threshold point from which it's going to change the state from VDD to VSS and VSS to VDD. In all such conditions, we have to note that this is a positive feedback. It's a positive feedback. It's not a negative feedback, or it's a Smith trigger whose output is either VDD or VSS. For small threshold point, it will make the decision to change it. So this is what actually we are doing it, right? So if your output is you are interested in output like VDD or VSS, one of the major criteria is keep your amplifier in positive feedback. Do not keep it in negative, and don't care about thereafter phase margin and all. Or you keep it in negative feedback but keep the phase margin more than less than 45 degree, where the oscillations are there and oscillations are grown up such that it reaches VDD and VSS. So there are two ways to make the oscillator. One of the ways is positive feedback. By the way, we don't want this. We want to study amplifier. We don't want to study right now oscillator. However, we will extend this theory to understand the oscillator. We are going to use positive feedback as well as some sort of negative feedback having phase margin less than 45 degree, and other controlling criteria like Bar-Cosin criteria we are going to implement so that the circuit acts as an oscillator. But right now our main aim is to make the circuit as an amplifier, not as oscillator. If you want that to have the circuit as an amplifier, you need to keep the circuit in negative feedback, and you need to make sure that its phase margin is greater than 45 degree, right? This is the golden rule. Please follow that. Now if you understand that, and this was just a background of the work, we are interested in negative feedback, by the way. And the whole chapter which we are going to study, it's on negative feedback theory, not on the positive feedback theory. The separate, actually, you can look at my other playlist where I'm explaining the design of op-amp, and the last lecture is on oscillator design, where you can study this. So you can look at my playlist, which is for the design of CMOS analog CMOS amplifier. In that, the last lecture of that one, or you can say that, or rather than calling it last lecture, because maybe I can add some more lectures. So lecture number 10, that's the oscillator. So it's almost like a 1 hour long lecture where you can understand the oscillator design. Notably, do not worry, in this particular course also I am going to explain oscillator maybe at the end of the course. So till now we have not reached that level. Right now we are still at negative feedback. So let's understand that first. And for that, I am following two books. But for this one, Microelectronics Fundamental by Behzad Razavi is the most important book for feedback. However, you can study the CMOS analog IC design by Behzad Razavi, same author. But this book is red colored and this book is blue colored. So I took some of the figures from this book to explain the theory. It's nicely written, and I must say that you can understand the theory in a better way from the reference number 1. If you understand that, and then you can actually move further for like some high level of understanding for feedback theory, then you can go there. Note that this feedback theory is negative feedback right now. It's not a positive feedback. Okay, so negative feedback system is the one where you are having following diagram, where X is an input. Let's make it in a better color. X is an input, Y is an output, and this output is being sensed by some feedback network, and its feedback to some summing point, and again given to the your original system, which was open loop. By the way, from here to here it was open loop. If it's not feedback with the negative sign, it's an open loop. Sometimes people do this also, that they are adding plus sign, so then it becomes positive feedback. And of course, if you wish to make the negative feedback system, it does not work the way you want, or you can say that you will end up with the output which is oscillatory, or it's a Smith trigger, right? Or you might have some hysteresis. All these things depends on what feedback network, how you are connecting. Sometimes some k is equal to 1 also. So it's a unity gain feedback but with a positive feedback, and this is known as comparison mechanism. If you look at the A1 is a feed forward system, and A1 is an open loop system also. Output is also having the sense mechanism because it's sensing the output and feeding back to the input just for the comparison. Notably, I am returning back to the negative feedback because that is what our main objective is, right? So if you want to find out what is A1, by the way, A1 and K are known as the transfer function, and we know that what are the transfer function? It's output divided by input. So in this case, if this is Y, and let's assume that this is X. By the way, X is nothing but X is equal to X minus capital X minus XF, right? So Y by X is equal to open loop gain or the feed forward system A1. In the case of the feedback network, y and xf are acting as input and output respectively. So xf divided by y is equal to k, and that's the feedback network. This is well known or understood theory. If you keep all these things somewhere and find out or interested in finding out the y by x, look at this, y is oral output, x is oral input, then that's known as the closed loop transfer function, because this is a closed loop or negative feedback closed loop system, where you must have studied in some course. If you have not studied, maybe it's a part of the course called control theory, where this is closed loop, where this is going to give you a1 divided by 1 plus a1k. I'm writing straightforward because I assume that it's very easy to derive also. If you wish to derive, you can find out from all these equations, where x is equal to x minus xf. You keep all these things one side and you derive y by x. So xf is already known, you just put it there and you can find out everything in terms of like y and x, and you can derive it. Or you can say that y is equal to a1 times x minus yk, and this becomes y plus yk is equal to a1x. Therefore y is equal to 1 plus k. So 1 plus k, I made mistake somewhere maybe. So y by xf by y is equal to k. So xf equal to ky. That's okay, fine. Yeah, so I forgot to add k over here. So it's a1k divided by 1. Okay, a1k divided by ka1. I have to take a1 here, right? So sorry, this is not. So this is the transfer function, which is closed loop, right? So in that case, you can see here, or you can remember such kind of transfer function. Those who have studied control theory, they know that it's a direct a1 divided by 1 plus k a1 for negative feedback. For the case of positive feedback, if it is positive, it becomes a1 divided by 1 minus a1k. That's the transfer function, and you can see the sign is changed over here. If it's negative feedback, it becomes positive, and if it is positive feedback, it becomes negative, right? This is already known. Okay, so what is the gain of such system when we have the negative feedback? That is a main point we need to understand first, because okay, yeah. So here you can understand that closed loop gain is a1 divided by 1 plus k a1. Let's keep it in somewhere in your mind. But before that, let's understand one more thing. That we started with this course with one fact, that I am going to make an amplifier which will be process voltage and temperature independent. Right? This is what we wanted. That it has to be process voltage and temperature invariant. So when you are looking at, let's say, for the case of BJT, you know, beta factor is there, it's the current gain. Even given in all the foundry manual, that beta is varying from something like 100 to 300. If this is the case, if I am applying some current called IB, the IC is varying from 1 to 3 times. That's a process variation, or the gain is varying. Similarly, if I am looking at a simple transistor whose gain is GMRO, now this GMRO both are depend on temperature, depend on the foundry, right? So different foundry means either you are in 180 nanometer, 130 nanometer or 28 nanometer, GMRO is decreasing with the smaller technology node. So you cannot guarantee that your amplifier will give you some particular gain. Generally GMRO in the range of 20 to 10 to 20 volt per volt. So this is also varying quantity. I don't want that. This is happening because my amplifier is in open loop configuration. It's not in negative feedback configuration, or you can say that it's sensitive to all these things. If I want to make it insensitive of all these things, what I can do, I can apply a negative feedback. You might have thought that when I was teaching this course, like very very first time, some of my curious students has asked me that if this V out by V in is minus RF by R1, then what's the role of this triangle? Of course, there is a role of this triangle because we are saying two things, that this is in negative feedback. If it is in negative feedback, we are going to follow the golden rule of op amp, which is ideal, and golden rule says that V plus equal to V minus, and I know that no current flow inside, no current flow inside. On top of this, there are also some more rules which are derived from here. These are the fundamental rules. Those are like gain is infinite. This open loop gain of op amp is infinite. Input resistance is infinite and output resistance is low, just to make sure that this is a voltage controlled voltage source. Yeah. So all these things are happening because of these hidden rules. Look, V out by V in is not minus RF by R1 always. It depending on these rules, right? And interestingly, after having the infinite gain of op amp, whatever the output you are achieving, it's coming only in terms of RF and R1. Notably, inside this amplifier, there are circuits like a differential amplifier, what we have studied. It is inside that. So what I mean to say, the differential amplifier or the folded cascade and all these other configuration, it might be cascade, or we are going to achieve some finite amount of gain. We cannot achieve infinite amount of gain. If it is finite amount of gain, this gain value will not be the exactly same. But if it is infinite, as we have already assumed, then it's only depending on the feedback resistances or the feedback elements. It does not depend on the open loop gain. You don't have to worry what is inside this, right? So by looking at that, you may make more insight on the fact that if A1 is infinite or tends to infinity, then the closed loop transfer function is equal to nothing but right, where this first term is going 0, by the way, right? and A1 is divided. So the closed loop transfer function only depends on 1 by k, or you can say that the feedback network may be made up of resistance, inductor, capacitor, whatever you like, you can keep it, and you can have the gain which is only depending on that. And on top of that, we also agree that we are going to make the things in ratio. If you are keeping the things in ratio, there are most likely the case that there is no variation of temperature or no variation of process, or that can be tackled easily, right? So the take home um, uh, take home conclusion is that closed loop transfer function, if it is negative feedback, is only depending on the feedback network, not on feed forward system. But the assumption is A1 is tends to infinity. One more thing here, 1 plus k A1, which is the denominator, let's call it denominator D, we are going to call ka1 as loop gain. If you look at this loop, in this loop it's k times a1, that's the gain observed by the entire loop, right? And let's make it short form as lg, not from LG Electronics, but it's loop gain lg. And lg loop gain, if it is much higher than 1, then what is going to happen to d? D becomes ka1, and from that y by x is going to be equal to 1 by k. So this is another theory. Rather than calling it a1 tends to infinity, I am saying that loop gain has to be sufficiently larger than 1. Then your output or the closed loop transfer function in negative feedback is going to depend only on the feedback network, right? So let's take this one as another take home summary, that loop gain is going to be much higher than 1. Then output will depend on the feedback network, on the applied input, of course, and it will not depend on feed forward system. By the way, this definition and all these things, all these numbers are relative. When we are saying infinite, actually it's not infinite, it's sufficiently large number, and that is going to be decided by your application. Slowly we are going to move on different real-time application of analog circuit designing, which is very interesting, like oscillator, ADC, DAC, or PLL. Then we have to define that number. That number has to be some some finite number, and above that number is considered as infinity. So that is what we are going to do, that we are going to set the budget, or we are going to make the required amount of gain, required amount of bandwidth, and other things, pole zero placement, all these things, we are going to do it accordingly, right? So let's start with the theory that loop gain has to be much higher than 1. Now look at one illustration. Now this illustration is the one where I need to find out the difference between V plus and V terminal, right? This is what I need to find out. By the way, difference between these two terminals are known as input offset voltage, or IOV. As per the theory, if A1 is infinite, then we are expecting X equal to XF, by the way, right? Both the terminal has to be equal, right? But let's, before going to this or understanding this, we can do following exercise. If there is an op amp, I am not connecting in positive or negative feedback, but I am connecting to two inputs. One input, let's consider this one as plus 15 volt, and let's consider this one as minus 15 volt, and this gain is right now infinity. Right now it's infinity. Then if I am applying here 1 volt, and if I applying here 1.1 volt, the output depends on one fact. It's V plus minus V minus times the gain of amplifier. That's the output. By the way, gain of amplifier is infinity. By the way, this one going to give you minus zero point 0.1 times infinity. So it might be like, you can approximate it to minus infinity. However, this particular amplifier cannot go to minus infinity, but it will limit itself to minus 15. So output will be minus 15. If I change it accordingly, output will be there. But what if I'm saying the gain is not infinity? If the gain is 10, what is going to happen? In that case, you have to replace this with the real number of gain. It's 10, so it's minus 1. So the output is minus 1 volt. It does not reach plus 15 or minus 15. But if I want this to reach plus 15 or minus 15, either, so there are two possibilities to reach this plus 15 or minus 15. Increase A. By the way, this is known as open loop gain. Open loop gain, you increase it for a fixed input, because you know that you want to detect which one is higher, 1 or 1.1 volt, and the declaration is only possible if you are declaring with plus 15 or minus 15. By the way, these two, this circuit is known as comparator, and these two labels are digital logic 1 and digital logic 0. I want to declare that which one is higher. So plus 15 means it's giving the green light and saying that yes, plus terminal is higher than minus terminal, and other way around. Or you can increase the input for a fixed gain, for a fixed open loop gain. So this is what you can do. If you are choosing first one, and if you are increasing this for detecting this one, or to take this one to plus 15 or minus 15, how much I need this one? I need this one, or the minimum voltage which I can detect. I am going to call it input offset voltage, by the way. So minimum voltage which can be detected, and we'll take it to plus 15 minus 15. It's known as input offset voltage. In that case, I need the gain of VDD minus VSS divided by the gain. Sorry. A is VDD minus VSS divided by input offset voltage. Right? So in that case, if this is 30 and I want to detect 0.1, I need to make the gain of 300. Right? Or if this is 0, I need only VDD by this one, then it's 15 by 0.1, and it makes it 150 volt per volt. So this is the minimum number which is going to make this amplifier number is like after 150 volt per volt is an infinite for me to detect 0.1 volt of input offset voltage, right? So 0.1 multiplied by 150 volt is going to give you either plus 15 or minus 15, but its minimum detectable input offset voltage is 0.1. Look at this with the first number of requirement. This is generally the most of the time that's the requirement, and you generally change with respect to the first one only. But if you don't want to do that, and you want to find out that, look, my gain is only 10, I can't do anything, so it cannot detect 0.1 as input offset voltage. What I need to do, I need to increase this, or I can find out how much it can be detected. So you can find out from this equation, and this becomes I of V is nothing but A VDD divided by A, where VDD is 15 and A is nothing but 10. So 1.5 volt, difference of 1.5 volt will be detected by this amplifier whose gain is 10 volt per volt. That is the meaning of this, right? So now all these numbers are depending on, or input offset voltage depending on what is the availability of the gain. So if there is a negative feedback, V plus does not become exactly equal to V minus, but V plus and V minus will have a difference of input offset voltage for the given finite value of gain. Remember this. It will be the golden rule over here. So here I know that it's not going to be equal to exactly x and xf will not be equal and opposite, right? By the way, this is now a negative feedback where x is applied at the positive terminal, and such kind of amplifier is non-inverting amplifier. Look at this carefully. Already we have seen it, and it's coming back, output is fed back to negative. So this particular uh, thing is known as negative feedback, but non-inverting amplifier. It's same as what you have studied, like this. It's negative, okay, and this is ground. Let's call it RF and R1, right? So this is the same circuit, but I kept it in different way just to start with. So here I already know that if A1 is infinite, gain is nothing but 1 plus R1 divided by R2. That's the gain. Using golden rule, I found out, because X is going here and you can find out the current flow from two things and you can find out the things, right? So you can find out the other things, you already studied that. But the fun is not there. Fun is there when A1 is finite number and I want that there is difference between V plus to V minus is equal to 1 by A1. So input offset voltage is 1 by A1 when the reference voltage is 1 volt. Let's assume that it's 1. Like digital logic 1, let's consider that it's 1 volt. So the things will become much more simpler, right? Okay, so now if that is the case, I know that every negative closed loop feedback system is going to have the gain of A1 divided by 1 plus A1k, right? This is known to us. I know what is A1. A1 is known to me. A1 might be some number, maybe 10 volt per volt, or if it is designed with differential amplifier, it may be GMRO, folded cascode, whatever it is, it will be depending on that, right? So that gain is known to me, but I don't know the gain, which is K, and K is nothing but XF divided by Y, because this is acting as a summing point or the comparison block, and here this is output is the sensing output node, and this R1 and R2 are sensing the things and giving back to the input. So in that case you can find out this in terms of R2 and R1. So XF is equal to R2 divided by R1 plus R2 times Y. So in that case XF by Y is equal to R2 divided by R1 plus R2. So you can replace that and you can find out the closed loop gain, which is this one. Notably, this does not have any information on A1, But A1 might be first order, second order, third order system, or having some poles and zeros, or having some much more complicated things. So if it is not dominantly single pole system, then this system have lots of problem. If you remember, if it is a second order system, inherently this whole thing is going to become an unstable thing. So we need to compensate them using Miller theorem, or many other compensation techniques are there, which is given in control theory, but which we are going to use it in analog very easily, right? So this is all about the feedback, and you can find out the rest of the things. So here the most important part is I want to replicate the signal at the plus terminal to the minus. I'm applying something here plus. When I'm getting it feedback, if you remember the negative feedback block diagram, it's getting replica at here, so that the out actually the difference of these two are exactly identical, and we are getting the zero output at the input of the feed forward system. So we need the good replica from x to xf, but that is not possible to have the good replica because everything is depending on open loop gain of amplifier. What we want infinite, but it's not infinite. If it is infinite, then x and xf are exactly same, right? And if it is that is the case, this becomes a non-inverting amplifier, which you have studied in your previous course, and it's very simple. It's 1 plus r2 divided by r1 divided by r2, right? But that is not happening. That's why the accuracy is playing role over here. So accuracy, and you can say that how much resolution you can have it, it's all depend on input offset voltage. And input offset voltage is nothing but, let's call it V reference, which might be VDD divided by A1, right? We are talking all these things at this low frequency gain, and from that you can find out the resolution. And maybe if you are implementing digital system, you can have the number of bits calculated from here. Maybe this is the next level of study, which will be part of DAC and ADC. We are going to study that, right? So as I told you already, the loop gain is nothing but KA1, and loop gain is not equal to closed loop gain. Remember this, keep it with the golden line and do not mix with that thing. Loop gain is completely different thing, and loop gain has to be much higher than 1, so that closed loop gain only depends on feedback factor K. And definitely we are going to make this feedback factor in a ratio, so that the answer is PVT independent, right? Because our main objective of the entire study is I want to make PVT independent, and I am going to make things in ratio, so that things will give us this output what I want. So if I'm asking you to make a system, or or an amplifier whose gain is 100 volt per volt, so you can, or maybe minus 100 volt per volt, you can do this one very easily, that the ratio of RF and R1 such that it's 100 volt per volt. Or maybe you can take non-inverting amplifier, and there are lots of things you can do, right? So, and the most important part is variations are quite uniform across different PVT corners. So if you are going in in ratio, then there is no problem. If K is some ratio, as we got it, R2 divided by 1 plus R1 plus R2 in the previous case, then the answer is same. Just to double check what we got is correct or not. So if this A1 is infinity, you can write down this, and this is becoming 0, and this becomes R1 plus R2 divided by R2, and that is become R1 divided by R2 plus 1. So this is same as what we were doing in this case, where R1 is in feedback, so R1 divided by R2, that's the gain in the case when A1 is equal to infinity. So we are getting the same result, by the way. Just for the sanity check, we did this, right? So we have to remember that loop gain has to be much higher than 1. Then y by x is approximately equal to 1 by k, and k has been chosen intelligently in ratio. So these are the things we need to understand, and let's keep it in your mind so that we can apply this theory in the real circuits. But before going that, when we are going to have the negative feedback, there are lots of other advantages which we are going to have it. We are going to study that, and then we are going to apply it on different circuits to make it in negative feedback for voltage control voltage source, voltage control current source, current control voltage source, and current control current source. So we are going to do it all these things uh, very systematically. But before that, just remember this: there are 4 kinds of structure of the circuit, and they are only defined by 2 things. So so in this case, if they are following this, they are coming under 4 different categories, which we already studied, and we are going to use this theory further in our negative feedback things. So thank you for today. We are going to study further things maybe in next lecture. Thank you.